Hi everyone, welcome to part 3 of lecture 1, and we will continue to introduce probabilistic models. And we will look at the probability axioms, but before proceeding it, I wanna explain some basic terminologies to help you to understand in a better way. Okay. So, as I said before, we have to select a sample space in a better way. Okay, and our sample space should be mutually exclusive and collectively exhaustive. Okay, so let me explain what are these things, and then I will try to explain the axioms, and then you can drive another some other rules by using that axioms. Okay, the first one is I say mutually exclusive. Okay, so mutually exclusive. So that's mean when I do a random experiment, I will get only one result. Okay, for example, so when I toss a coin, I cannot get the head and tail at the same time, right? I can get head or tail. So there is only one result. Or the rolling die example. So is it possible to get one entry after a random experiment? I mean, after rolling a die, it's not possible, right? So I can get only one, and I can get only two, etc. So I can get only one result. So if your sample space satisfies this rule, I can say that sample space are the mutually exclusive. This is the important thing. And the second one is collectively exhaustive. So collectively exhaustive. Okay. So in this case, let me say I have an experiment. This is an the region of the experiment, let's say, and this part is event 1, and this part is event 2. And also, I need to have an event 3. So the sample space that consists of should consist of all the events. Okay, in other words, the union of the events should create our sample space. So let me give you a more concrete example. Let's say I have a die. Okay, so let me draw it if I can do it. Let's say it's not good, but it's fine. Let's say this is a 1 and this is 2, and there are some other part on this side. And let's say this part has no any number. Okay, so when I roll this die, let me draw the sample space region. Okay, so let's say event 1 is 1, event 2 is 2, event 3 is 3, event 4 is 4, and event 5 is 5. And let's say the number 6 is missing. So the union of these events is not creating the sample space, right? So there is some empty thing here. So this set is not collectively exhaustive. So so in a summary, I can say that if the union of events simply creating our sample space, I can say that the sample space is collectively exhaustive. So if these are the case, I mean, if our sample space is mutually exclusive and collectively exhaustive, we can talk about the axioms. So, okay, let's start the axioms. So axioms are accepted as true. Okay, we are accepting these rules as true, and by using these axioms, we can drive some other, let's say, sub-axioms or some formulations, some operations. Okay, the first one is the non-negativity. So I can say that the probability of any event should be greater than or equal to 0. Okay, so the probability cannot be negative number. Okay, so this is the first axioms. And the second one, if the events is the sequence of a disjoint events, then I can say that P union, the probability of union of the events is equal to the sum of the individual probabilities of the events. Okay, so this is our second axioms, the additivity axioms. And the last one is the normalization. So the normalization means the sum of the events, the all events, the probability of the sum of the all events should be equal to 1. In other words, the probability of the omega, means the sample space, is 1. Okay, so and by using these axioms, I can drive some other formulations. So let me look these ones. Okay, so as we said before, an axiom is a self-evident or universal recognized true. So we accept these things are true, and then we can derive some other properties. For example, let's say the first one is PA, the probability of event A is equal to 1 minus probability of A complement, right? So in this case, in my sample space, there is a one event, which is A, and PA, and the A complement, PA complement, I mean A and A complement are the disjoint events, right? Like, let me create another whiteboard. So let's say this is my omega, and I have only one event A, and this part is A complement, right? So A and A complement are disjoint events. That's mean there is no any common points between A and A complement. And I know from the axioms, sorry, where is, so the sum of the events, sorry, sum of the disjoint events is equal to union of them, right? So in our example, A union A complement, right, is equal to 1. Why? This part is actually our omega, right? And from the normalization axioms, we know that the probability of omega is a probability of sample space is 1. So I can say that now, and this is equal to PA plus PA complement is 1, and I can say that PA is equal to 1 PA complement. Okay, so what we did, we derived this property by using two axioms. So another one is the empty. So probability of empty sample is 0 because we know that our sample is collectively exhaustive. So there is no the empty events, right? And I know that. So that's why getting the empty space, the probability of getting empty space will be 0 because we are working with the collectively exhaustive data set. And also I can use these axioms here and plus I can say that one. And I know that until here, this is the omega and this is the 1. So, and also this is the 1 plus 1 plus p empty space is 1 is equal to 1 plus probability of empty space, and it should be 0. Okay, so I can use the additivity and normalization axioms to derive this property. So another way, way of thinking can be the omega in empty space are disjoint events, and then I can derive from this information. I can use the additivity axioms and the normalization axioms, and I can derive that property. So let's look at this one. If if A is subset of B, then I can say that probability of A is less than or equal to PB. Okay, so let me draw this one. Okay, let's say I have a sample space and I have A and B, right? So, but in our property, the A is a subset of the B, right? So this will be like that. This is a B and this is an A. Okay, so in this case, we are saying that the probability of A is less than or equal to PB, right? Am I right? Yeah. If this is the case, actually there will be no equal sign, right? But if let me change the line. If the relationship between B and A is like that, this is the B, and let me change the color. And also this is an A. So in this case, the B and A will be equal. So that's why the probability of B and A will be equal. Okay, so you can derive this property from you can prove this property by using just the Venn diagrams. Okay. So let me. Okay. So another one is again the union of the events should be less than or equal to individual sum of the probability of the events. So, but if you remember, we say that in the additivity axioms, the union of the probability of the union of the events will be equal to the sum of the individual probability of the events. Yeah, right? So why we use this one? So less than or equal. So let me show this property by the Venn diagram. Okay. So this one. Okay. So this one. Let's say we have two events. Okay. So This is our omega sample space. And let's do this. Let's do this for the disjoint events, like this is an A and this is a B. Let's say the probability of A is A, some non-negative numbers, and let's say the probability of B is B. So what the additivity axiom says, P A union B is equal to P A plus P B, right? So the A union B is equal to A plus B, and what's the PA and PB is B. So that should be equal, right? So now let's consider not disjoint events, okay? Not disjoint. So that's mean there will be some common points, right? Let's say this is A, this is B. Let's say this part, the probability of this part is A, and intersection of the A and B, let's say this is B, and this part, the A complement, I can say, or I can define this part as and A complement, right? So omega intersect with the A complement, this part, and let's say this part is C. Okay, now I know that the P A union B is equal to A plus B plus C. But if I sum the individual probabilities, I mean the PA plus PB, this time I will get A plus B, this is for the A, and plus B plus C, and this is for the B. And this one is equal to A plus 2B plus C, right? So A plus B plus C is less than A plus 2B plus C. That's why for the general situation, I mean, this is this rule for the disjoint one, but for the general one, we have to add an equal sign. And that's why we are saying if, sorry, this one, if, so I mean, we can use this formulation, the less than or equal to for the general events, general events, not only for the disjoint events, okay? Okay, and this one is the inclusion and exclusion operations, and let's say the union of the different events is equal to sum of the probability of the individual events minus two events intersections, and plus 3 events intersection minus 4 events intersection plus 5 event intersection. So let me prove that one. So again, let me create an events, and let's say we are working with 3 events, okay? And let's say this is an A, this is a B, and let's say this is a C. And give some numbers to define the probabilities. I mean, this part is A, this part is B, and this part is C, this part is D, E, F, and G. Okay? So what the properties say us Let me check one. Okay, so union of the events. So E is equal to 1, 2, 3 in our sample, and this is an A1. So let me define this. This is an A1, and this is A2, and this is an A3. Okay, will be equal to PA1 plus PA2 plus PA3, and then check the formulation again, minus two events intersection of the two events. So each pair of the events. Okay. So what will we do is minus probability of A1 intersect A2 minus probability of A1 minus A3 and minus probability of A2 intersect A3, right? And the last one is the plus 3-event intersection. So that is the probability, let me write here, plus probability A intersect A2, A1 intersect A2 intersect A3. Okay, so let me write this thing. The first one, this one here is A plus B plus C plus E plus D plus F plus G. Okay, so I should get exactly the same summation from this formulation. So what is the PA? PA is A times so AA plus B plus E plus D. And what is the PA2? Is B plus C. I mean, I'm looking this part, okay? And plus D plus F. And A3 is A plus D plus F plus G. And this part is, okay, this part is done. So look at this part, this one. A1 intersect with the A2, and this is an minus B minus D, and this part is this one minus E minus D and minus E, and the last one is will be intersect with A2 and A3. This one D and F, so minus D and minus F, and plus this one. So intersection of the three events, that is the D, right? Plus D. Okay, so these are eliminate each other. This one, this one. So this one and this one, this one and this one. This is D, right? This is D, and this one is this one. So what are left is A plus B plus C plus E plus F plus G and plus D. So if you compare this one with this one, you will get exactly the same summation. Okay, so that's why we are using inclusion and exclusion operation in this kind of events. So, okay, please redo these things by yourself just to to understand better and to make it more concrete. And also, you are not limited to only these properties. You can extend your knowledge, or you can derive some other properties to use in the probability models. So let's continue. So let's go to the discrete models. So if the omega, I mean our sample space, is countable, that means we have a discrete model. Also, we will work with the continuous model in the lectures in the future, but now let's go with the discrete models. So if the samples, if the sample space is countable, we have a discrete model. But what the countable means? It means that you can enumerate its element as a list, as a list. So what I mean is you can map its elements to the natural numbers in a one-to-one fashion. What I mean, let's say I have the set, okay, 2, 4, 6, 8, and it's going. So I can say this is the first number, this is the second number, this is the third number, this is the fourth number, and I can go wherever it's go, okay? So I can enumerate them. So if this is the case, I can say that my set is countable, and I have to work with the discrete model, okay? All finite sets are countable. So if you can count all the elements of the set, I mean, it's if that's a finite, so I can say that's the countable. Infinite sets may also be countable. In our example, let's say there's even numbers go infinite, but even if it goes infinitely, you can still enumerate them, right? So you can say this is the first number, second number, third number, and until some points we cannot define, but still you can enumerate them. So natural number, yes, infinite sets may also be countable, and these are the examples, right? Okay, so but be careful with the infinite sets. The truth may be different. I mean, it can be different what you think. So let's say the A is 1, 2, 3, 4, and it's going infinitely, and the B is 2, 4, 6, 8. So whose cardinality is larger? I mean, let's say, let me ask you in another way. How many elements you can count here, and how many elements you count here? And which of the events has more elements? Actually, it's exactly the same. So what I mean, actually, no matter where they start or how they go, they are even number or odd number. I mean, it's not matter. They will go infinitely. So that's why they will have the same number. Like, let's say the first event has something like that, okay? There are some numbers here, like 2, 4, 6, 8, something. And let's say the other one is like that. So I can say that, let's say this is an A and it's a B. I can say that B has more elements than the A. I can say that. Why? Because let's say you are, so let's say you combine these things like that. So you can match each element of A with each element of the B, like there's one, this, and this. It will go infinite, okay? And the last one will be this one. I mean, actually, there will be no last one because these are the infinite numbers. But I mean, you have to understand this concept. Okay, if there are two sets and they are infinite, we cannot say that the A has more elements than B, or we cannot say that B has more elements than A. So if there are two infinite sets, we can say that they are exactly the same number of elements. Okay, they have same number of elements, the exactly same number of elements, and their cardinality is equal. So, so if the omega is countable, actually we can specify the probability law by the probabilities of events that consist of a single element. Okay, so we will simplify these things, but each outcome takes its mass actually. So before going to this formulation, I just want to mention that this is actually a set function. So the correct notation actually should be this one. Okay, the rounded braces inside the curly brackets, not this one, but for our convenience, we are gonna use this one. Okay, so this one. So if the omega is countable, okay, and if the model with a finite sample space, like the magnitude or cardinality of the omega is, let's say, n, where every outcome has equal probability. So this model is called discrete uniform. So discrete uniform. Uniform means that each event can be equally likely, okay? Like, and if I graph that one, that is something like that. Everything, so each element will be same probability, okay? Same probability. So this is like tossing a coin. So, I mean, do you think, can I say that the probability of getting head will be greater than or less than, no matter what's that, from the probability of the tail? Do you think, can I say that? No, I cannot say that. They are, actually they are the same, okay? They have the equal probabilities. So each outcome has the equal probability. That's why, if this is the case, I called this model discrete uniform model. And why discrete? Because these are the countable ones, okay? And discrete, countable, and finite sample space, discrete uniform model. So in this case, if this is the case, I can simply calculate the probability of an event by simply the magnitude or cardinality of the A divided by N. I mean, give me some examples and you can understand in a better way. Let's say, again, die example. So what is the possible outcomes? Possible outcomes is 1, 2, 3, 4, 5, and 6, right? And let's say the A is getting 2 events, okay? So how many elements will be for in event A? It's 1, right? Because there is only 1, 2. Okay, this is the 1. And what is the cardinality or cardinality of the sample space or the total number of elements? That's a 6, right? 1, 2, 3, 4, 5, 6. So I simply can calculate the probability of the event A, and the event A is defined as getting 2 is 1 over 6. Okay. So let me give you another example. Let me create a whiteboard. Let's say, again, let's go with the die example. So possible outcome is 1, 2, 3, 4, and 5, and 6. Okay. So let's say let's say I roll the die 2 times. Okay, this is the first roll, and this is the second roll. In the first, let's say we define an event A, and event A is the total number will be, let's say, 5. Okay, so for example, if this is the 1 and this is the 4, these results will be in A. And if this is 2 and this is 4, this will not be in A. Okay, and if this is let's say 2 and 3, this will be in A. And how many different pair of the results can we get? This is 6, right? 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, etc. So we can get 36 different pairs. So how many of them will be in A? 2 of them, I think, right? 1, 4, and 2, 3. There is no any other option. So, sorry. A is going to be 2, and omega is 36. So the probability will be 2 over 1 over 18, right? So this is how we use this formulation. If the if our sample space is finite and every outcome has equal probability. Okay, so if this is the case, this model is called discrete uniform model, and if we are working with the discrete uniform model, we can use this formulation to calculate the probabilities. So this is the case. Okay, so here there is another example. I mean, actually another question, and the question is, what's the probability of getting full house? I mean, this is a card game, and there's a term there, full house, and it is a tree of kind and plus a pair. So let me show you the cards. I think there are some. Okay. Okay, so these are all the cards. Okay, and let me also show this one. Small. Okay, so in a card game there are 15 different cards. Oh, sorry. Why it's not that? Okay, so there are 15 different cards. Okay, and 4 suites, and this suite is called spades, hearts, diamonds, and clubs, and each suites have 13 cards. So the total cards is 52, and 13 of them belongs to one suite. Okay, and what is the probability of getting a full house? I mean, you will choose 1, 2, 3, 4, and 5 cards, and 3 of a kind. I mean, it can be, for example, the Hearts King, Diamond Kings, and Club Kings. Let's say K, 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 and a pair, like let's say 10, 10. This is just one example. Okay, and this can also change, like let's say you can get 8, 8, 8, and 10, 10. Okay, so what is the probability of getting a full house in a poker game? Let me remove these ones. So okay, this is the answer, and we solved this in the classroom. But to try yourself, please try to solve these questions to make sure you understand the concept of the discrete models. I mean, it is not easy. For example, this part is used to calculate how many different the mix of 5 I can get. Okay, how many different combinations I can create. So, for example, one combination can be 1, 2, 3, king, 10. For example, this is a one combination. So this part is used to calculate how many combination of the 5 cards I can create. Okay, this is the one. And please try to understand this part. Okay, to calculate the probabilities. And simply this is the A, and this is the omega. Okay, so we, as I say, we will continue to, we will solve this problem in the classroom. And let me show you another question. This one is what is the probability of getting a 2 pair? In this times, you will choose 5 cards, and 2 of them, this one be pair, and this one pair, and this can be any other card. Okay, for example, this can be 7, 7, 8, 8, and king, or this can be 10, 10, king, king, and queen. So all these things satisfy this 2 pair condition. Okay, so the question is, what is the probability of getting a 2 pair? In this case, again, I will create the 5 of them. The mix of 5 cards. So this part is again my omega, and this is the results of this calculation show us how many different mix of 5 cards. Okay, so by using this one, I can calculate the different combinations. So, and this part is the actual number of 2 pairs. Okay, total number. So we will solve these questions in the classroom.